Good day everyone. Myself Aditya Nigam. Today we are presenting our work on iris based recognition system. In this work we have used two feature extraction technique. First one the DCT based transformation and the second one the relational measures. Along with me the co-authors are Dr. Falguni Gupta, Balendra and Jyoti Triya. Here this is going to be the outline of our whole talk, in which we'll talk about the introduction, advantages, motivation, strategies that we have used, the proposed methods, experimental result and conclusion. So with the starting, I just wanted to state that till now everyone knows that iris is one of the best biometric trait available in the business, and the reasons are very obvious. It is unique, it is stable, non-invasive and several other reasons. In this figure I just wanted to let you know that this is an annotated figure in which what are the basic anatomical features which are available within an iris. So here you can see that this is the eyelid part, these are the eyelashes, the black parts. This white region is being called as the sclera, the internal black region which is being always termed as the pupil, and within pupil and sclera the whole region, this whole donut one can say, this is being called as the iris, which is assumed to be very unique. So the advantages of using iris biometrics are that it is universal, very high accuracy it has, non-invasive, stable also, it remains, they are not being changed very fast within some span of time, also acceptable, tamper resistance, as well as it is very fast. I mean, this system can be deployed and can give you a result of one matching very fast. The motivation here is that, as I've told you, that the iris texture is very stable, and it's being developed till our very early. One can say that up to an age of 2 or 3 it's being completely developed, and after that it's not going to be changed much. Also the pigmentation, our iris pigmentation is more or less similar, it's not going to be changed for a long period of time. One important thing about an iris is that it is an internal organ. Being an internal organ, and our whole body is having a natural state in which whatever the effect or any harm which is being posed on our iris, our body is in a position to handle it in such a way so that minimum harm is being done on our iris. So because of an overt internal organ, it is well protected naturally. And it's not the case with all the biometrics. If I take the example of fingerprint, you have to use your hand, and if you can go and see the fingerprints of farmer or the persons who are doing very hard labor, their fingerprints are completely worn off, and this is one important edge that we can see, that iris of most of the persons are usually in a very good condition and can produce a very good quality. But also, being all these positive things, there are several challenges, including good quality iris acquisition. So not much, as you can see that you can't control the motion of your iris with a very high accuracy, and this is precisely the thing which is coming into the picture, that user require a huge amount of cooperation when he wanted to give a good or a high quality image acquisition. This is a problem. Other than that, motion blur will also be there, because it is not on your control to basically control whatever the motion of your eye. You can't fix up the motion of your eye, and because of that there will be some amount of motion blur always available in your eye that one should have to deal with. And the biggest problem in any iris recognition system is the different types of occlusion that we can have, and these occlusions are here, as you can see that this is the complete eye, but at least this much amount of iris, it's not the complete iris which is being visible. Some amount is occluded because of eyelid, eyelashes, as well as this specular reflection. So specular reflection is not over the iris, but sometimes it may be over the iris, as well as this specular reflection is going to create good amount of problems when you wanted to segment or extract the internal donut of this iris, complete iris when you are extracting. That's called as a segmentation. So these are some of the challenges that one should have to deal with. This is a general iris recognition framework in which image is being acquired. First it's being segmented. Once you got the segmented image, it's being normalized. Normalized images are being enhanced and occlusion masking is being done. Occlusions are being masked in order to, you know, estimate first that what are those regions which are being affected by the occlusion, and later when you are extracting the feature, any feature which is coming from this occlusion, we don't use that feature while we are matching here. So before feature extraction, occlusion mask is being computed, features are being extracted, and while matching we just see that whether this feature is extracted, which is being extracted, is it belonging to an occlusion. If it is coming from an occlusion, we are not going to use that feature. And once you got this matching, I mean two images, one from the database, one for the feature, that the actual image that you have got, both of these features are being matched, and a single decision module is being used to see that whether this matching is being accepted or not. The strategy here we are using is that we are using two features, feature 1 and feature 2, and both of them are extracted from the single image, and using two different matching schemes we match them. We got out these scores, two different dissimilarity scores. They are being fused using some weighted mean, weighted averaging model, and then a decision is being taken that whether you are going to accept it or reject it. Okay, so this is the full architecture of our scheme, our proposed scheme, in which the images are acquired, segmented, normalized, occlusion mask is being created, then they are being enhanced using the Clahe based enhancement, local enhancement technique, then the features, first DCT and the relational measure, that is the RM that we are about to discuss. Both of these features are being computed, they are being matched, score is being computed, and then it's being given to the fusion module to get a single fused score, which is being used to decide that whether this matching is accepted or rejected. So the first step is segmentation, normalization, and occlusion mask detection. So here if you just see that during the using the images, I just wanted to explain that this is the original image. Well, first we threshold this original image, over that we apply the Sobel edge detection to find out what are the edges. So here you can see that you can get this center circle. So that is being, and it's a very hard center circle because it's a circle which is denoted to the pupil part, and it is very, I mean there is a very hard edges which are being available. So Sobel edge detection can detect that, and over that we apply the Huff based transformation, which is a voting scheme, which is going to give us the internal circle. For the outer circle we use the integral differential operator, which is being widely used. So integral differential can give you the outer circle. Once you got the inner and the outer circle, basically the centers of center as well as the inner and the outer circle, the whole one circle. So we started to think about the first circle, the second circle, the third circle, the fourth circle, and for each circle it's an spatial the spatial coordinate system. We convert it into the polar coordinate system, and in the polar coordinate system one circular ring can be seen as a single straight line. So for every circle that we have here, that is a circular annular ring, it's being represented in the normalized image as a single straight line. So our whole this donut, if we say that's a single donut, it's being converted into a normalized rectangular strip. Over that we also apply the occlusion mask, which is basically iterative thresholding, so as to get the two different clusters, one which is belonging to the iris and the other which is belonging to the other things which are there other than the iris. So this is the occlusion mask. These points which are high or 1 here, this is the binary mask. The points which are high or 1 here are suggesting that this is some occlusion which is being available. So we just think about that when you are extracting the features, please don't use these those features which are coming from occlusion. Then the next step is denoising and enhancement. So again via images I wanted to explain it to you that this is the normalized image, initially it's being denoised using Wiener based filtering, because it may be having several different types of image based noise. Once we got this, the average background illumination is being extracted, and it's being done in such a way that this image is being divided into blocks, for say 4 by 4 pixel of blocks, and each and every block, so for every block we have to compute that what is the average value of that block. Once you got that average value of that block, we subtract that mean with that block values, which is basically removing the mean from all the pixels of that block, and in this way, so for every block we find out the mean, subtracted it with the all pixels gray value, which is going to give us a uniformly illuminated image that you can see here. The illumination of this image is better than the previous image, and then so this is basically, that is why it's being called as a local enhancement technique, and then over that we applied a Caip based enhancement. So this is the final enhanced image. Now this is the first feature extraction technique that we are using. So here we have applied the discrete cosine transformation. So as you know that the basic property of discrete cosine transformation is it's being used for JPEG compression. When you have a one-dimensional feature vector, we apply over that the DCT transformation, which will actually convert this signal into most of the important coefficients will actually be having non-zero values, and other coefficients which are not having that much importance, they will be having values which are very close to zero, and we are not going to use those values for our features. So here one can see that the whole image is a two-dimensional feature, but we have used a one-dimensional feature vector. So how we have constructed a 1D DCT coefficients, it is that we divided the whole image into blocks like this, and these are the overlapping blocks. One can see that this is the first block and this is the second block. So there is this much amount of image region which is being overlapped. So this is the overlapping, and why this is being overlapped, because there may be occlusion because of which this block may not be used, but some part of that block which is being overlapped with some other block, and it may not be having occlusion. So because of that, at least some part of that block which is being occluded is being used to ensure this thing. Now here you can see that how the feature is being extracted for one block. So for this block, for every for every column which is there, so there are total n columns, because it's the length of this block is n. So for every column we compute the average. So for this column we compute the average, for next column we compute the average, and in this way for one block we will be having because we are having n columns, we are going to have an average n values, n these averages. So the one can say that the feature vector that we have got is the average value of that column and n such values. So it is basically n-dimensional vector, one-dimensional vector of n units for that particular block. So from here I just wanted to use again the figure to explain that how we have computed our feature vector. So this is the enhanced image just we have talked of. Over that we apply our enhancement that we have done over that before. So after this enhancement, the whole image is being converted into the DCT compatible domain, DCT compatible image. So DCT can work well and effectively give you the result when the values are in between 127 to 128. So basically negative and positive both ranges are present, then the performance of DCT is observed to be very well. That is why we subtracted the whole image by 128 just to visualize that this can be now be seen as in this way. Not much significant variation is being done because it's only a linear operation. After that for every block, as just I have told that we have done the blocking in this way, for every block an n-dimensional feature vector is being computed, and this can be seen as this. So this is an n-dimensional feature vector. Over that we apply the Hanning window, which is basically to see that if there is some spectral leakage, if it is present, then Hanning window will take care of that, and this signal will now be converted and seen as this feature vector. So now over this one dimensional feature vector we applied the discrete cosine transformation, and we will be getting one dimensional DCT coefficients which are represented like this. Some DCT coefficients may be positive, some may be negative, and we then apply the zero crossing, which is going to give for every block a 0 1 feature vector, and in this way the whole image is being tessellized, and for each block we find out that what is this feature vector and concatenate that. Later we use the Hamming distance to find out the difference or the dissimilarity score. The second method is the relational measure. So just to explain this relational measure, I would like to use this figure. So here if you see that in the relational measure basically mean to say that what is the relationship of one pixel to another pixel. So instead of a pixel we started to talk about a block. So we take a block here, take 4 neighboring blocks, apply a Gaussian filter over that block. So this whole block of say n by n pixels is going to give you one value. Similarly you got these 1 2 3 and 4 top, down, left and bottom. So for every block we try to find out that whether this value, the response, the Gaussian response of center block is greater than or equal to the top block or less than the top block. If it is greater than we take as 1, if it is less than we take as 0. So in this way for every block we can find out 4 different binary values. So basically for every block the signature or the feature vector that now we will be seeing as it is 0 1, but 4 different values. So so once you got this feature vector for the every block, we again concatenate that. It's going to give you a feature vector related to that, and then you know, just we apply the Hamming distance to find out. Before finding out the Hamming distance between the two such feature vector, we take the first one and the second one to with which we wanted to find out the distance. We can also you know, rotate it left or right so as to counter any alignment problem which is being there. So we just do some left and some right bit. So basically we take a probe, match with the gallery template with its shifted versions to left and to right to find out the minimum distance. So that is the minimum Hamming distance that we will be using. And later when you find both of these features, both of these scores, then you fuse both of them depending upon the accuracies of the individual systems, and individual score is being computed. So here you can see that these are the images of the 3 databases over which we have worked on: the KCI interval, KCI lamp and IITK database. And these are the CRR and the EER of the simple, the first extraction technique, feature extraction, that the DCT extraction. So for CRR is 99, 98 and 98, and the equal error rate here is shown as 1.81 for the interval. LAMP is a very difficult database, having very huge amount of variation is available. So because of that one can say that higher equal error rate is seen there. These are the ROC curves. One can see that here this is for the KCI interval, LAMP, and for the database. So this is the EER ROC curves, and this is the genuine and the imposter distribution for the one-dimensional DCT. Here you can see that these are the scores that we have got for the relational measures, and you know, here you can also see that these are the equal error rates of the relational measures that we have assumed, and this is the genuine and the imposter histogram. If you wanted to compare, the best thing is that you can plot the FER and FRR over one graph. So here you can see that this is the proposed DCT, blue color, then the relational measure which is in red color, and Gabor filter which is in the which is the we wanted to compare. It's being way back defined by the Dogman. So here you can see that the one which is the lowest one is the best one. So you can see that the fused version is going to give us the better performance, even better than the DCT, RM or the Gabor one. This is so this was the result over the interval database. This is the result, the same result but over the LAMP database, and these are the results that we have got over the IITK database. and just wanted to ensure that the whatever enhancement that we have done. So this red curve is showing that when we have not used any enhancement, and blue is showing that once we have used the enhancement. So you can see that the enhancement is going to let your performance better. These are the references. Thank you.